Recording is rolling. It is Tuesday, March 10th. So I'm going to walk you guys through change of phase. So the video that's uploaded yesterday to Google Classroom, I got the solution written out right here. I'm going to walk you guys through, remind you guys how that works. Right, see the numbers? Right. This is going to lead into pressure, temperature, phase diagram with the water. You guys see what triple point is. And you guys have your laptops out ready to go because after all this, pull up a computer on thermodynamics. Okay. And then tomorrow I'll see you guys, but Thursday I have a jury summons, so I won't see you guys then. Yeah, and then yeah, I guess I won't see you until Monday after that. Okay, so uh, I'm gonna give you guys a packet of thermo puzzles that you guys can work on with each other. Okay, so it'll be team puzzles, and then some of the questions are gonna look like what I'm about to recap with you guys right here. Okay, right, so say you got a block of ice. Okay, so make the mouse here, 2.4 kilograms block of ice. Let's say you pull it out of the freezer and it's -5 degrees Celsius with the temperature. And how much energy would it take to say boil it away? Well, to boil it away, we got to go through several steps. And here's the steps. First, we got to bring the ice to melt, then melt all the ice, then bring the water to a boil, and then boil all the water into steam. And there's a nice picture that goes with those four steps. And here's the picture. Well, I can't fit it all on the screen at the same time. Are you guys okay with the word so far, the concept? Okay. Here's the picture version. Right, so here's temperature versus heat energy for water. Okay. And you can see different phases of water. Here's solid, as in ice. Or here's liquid, like liquid water. And here's the gas form water, like steam. Right? And the phase transitions are these flat parts of the curve. Because during phase transition, here's the melting and here's the boiling section. Notice that the temperature is stuck in each of those cases. It's like stuck at some value. And the temperature doesn't actually change until right, you completely change phase and then you can change the temperature off that. Right? So this part of the story, we're taking a cold ice cube out of the freezer. We got to bring it up to the point where it begins to melt. And then here's the whole melting process. Right now we got a puddle of very cold water. Now we're bringing that water up to a point where it can begin to boil. Right now here's boiling, boiling, boiling. Now it's boiled all the way right here. And that's the end goal for this question. Okay, so you guys good with that? Okay. I remember in class yesterday, it was like it's a little tight fit, and the thought start reading. So I can solve this with two formulas or these different sections. So first is this diagonal part right here. I got to bring the ice cube up to no, guys. If we're calculating how much energy it takes, but before I go plug in and check with all the equations, okay, guys, what's the most energy intensive part of this process? Guys, where's most of the energy going? Is it going into which would be how far do you move right on the graph, right? Is it bringing the ice to begin to melt, melting the ice, bringing the water to boil, or boiling away all the water? Which just takes the most energy? Yeah, definitely this stage right here. Okay, that's going to definitely dominate this whole process. All right, so just keep that back in mind. Let's run the equation. So we got delta Q equals MC delta T. Guys, delta Q is a transfer of thermal energy. Transfer of thermal energy. Right? That's also called heat. Right? Heat is a transfer of thermal energy. Okay? I'm going with the 2.4 kilogram block of ice. Now, the specific heat capacity of ice is a number you would have to pull from somewhere. So I got it right here. Okay. It's 2.09 kilojoules per kilogram Kelvin. It tells you how much energy it takes to raise 1 kilogram, 1 Kelvin, or 1 degree Celsius, you could say. Okay. So we've got a number back here. Okay. And then the change in temperature. If we're going from -5 degrees to 0 degrees, that's a change in 5 degrees Celsius, right? Which is also a change in 5 Kelvin. It's a change, that's good. So I mean, some number of joules out of that. You guys get that? Some number of joules? Right, so I write that number down. That's the first of a four-part process. Okay. Now we brought the ice cube up to begin to melt. Okay. Now we got to melt it off, which runs into a different looking equation. As this looks different than before. Okay, see that? So you guys either have the same address from yesterday or you're jotting some stuff down now. Okay. Because when you get to those Thursday puzzles and there's a substitute, you guys are helping each other out. It's going to be the same type of equations. Okay, so the melting part is anything is flat like here. Got delta Q equals M delta H. Okay, so here's the mass of the ice cube. I'm going with 2.4 kilograms. Okay. And then delta A diffusion. Okay, so there's one value that applies to like melting, right? And another part that applies to boiling. It's different numbers, right? Basically, you can think of it this way: like how long is this little flat curve right here? How long is that? Right. So for this water going from ice to liquid, it's like 334 kilojoules per kilogram. Right? Now, guys, 334 kilojoules. What does kilo mean again? Kilo is a factor of a 1,000. Okay, so I went ahead and just expanded to joules per kilogram Kelvin. So space, that's how you get it. So you guys see I tag on 3 zeros per thousand. Okay. Anyway, run that, 2.4 kilograms. Okay, I get a different bit of energy. Okay, so now we got part two. Now we've melted all the ice. You guys see that? We melted all the ice. We have very cold puddle of water. Now we're into this part of the curve. So now we're going back to MC delta T. So now its transfer of energy is MC delta T. Right, so same mass as before. Right. Now, this number for water might be a good number to know because you see us all over the place in different science classes. Right, so this is specific heat capacity to water. By the way, I should tell you guys, because if you put a pot of water on the stove, what heats up way faster? The water inside the pot or the metal of the pot? What heats up way faster?
Metal.
Yeah.
Metal.
Yeah, the metal you guys are saying? Yeah, right. And numerically, what that means, or how that shows up here, is that water has an extremely high heat capacity. Like if I look at steel, let's look at steel. So say a pot made of steel. You guys see how small that number is right there? Right? That means you put in a little bit of energy and the temperature changes real fast. But water, right? Guys, water is like almost 10 times that of steel. That means it's like 10 times the difficulty to change the temperature of water. You guys see that? You guys see that compared to metals? Right. Right. Anyway, we'll run MC delta T. Same as before, let's give a heat capacity of water. We're changing water from 0 degrees to 100 degrees Celsius. That's a change of 100 degrees, 100 Kelvin. Right? Here's how much energy it takes. Right? And finally, the last part, we got to boil all that water away. You guys just told me this is going to be the most energy intensive part of the process because we're moving furthest to the right of the graph, heat energy. And here's the heat of vaporization of water, 2265 kilojoules per kilogram Kelvin. So again, I took kilo multiplied by 1,000 here. Right. Yeah, it's the same mass of water. Right. And it takes this much energy in joules. Okay. Now, to get the total energy for that entire 4-part process, all I have to do is add up the 3 parts that I circle, or the 4 parts that I circle. So this part, this part, this part, this part, and I just write it right here. I said the sum of the transfer of thermal energy, and I typed it on my calculator, and I got 7 million something joules. Okay. You guys see that process? You guys see it conceptually? Is that right? Okay, so you think you could solve this also when you get the packet of puzzles? All right. So of course that's all recorded. You guys have access to the video. Right. Okay. Next thing I want to get into is there we go. You guys see this 100 degrees Celsius that water boils? Okay. Really, that's only true at sea level. Now, what do you guys think way up in the mountains? I suppose you go up into the mountains, like Denver, Colorado. The air is really thin. Do you think it takes more pressure or less pressure to boil the water? The higher temperature or lower temperature, I should say, to boil the water? Let me see. Show of hands. How many of you think in Denver, Colorado? So everybody, has anybody ever been up to the mountains? Like Denver, Colorado, maybe? Yeah. Yeah. Okay. Yeah. Been to Denver, and if you like try to run around, you'll lose your breath really easily. A lot of Olympic athletes like to practice up way up in the mountains where the air is thin because their body acclimates to having very little oxygen. Right? Right. So, show of hands. How many guys think that up in Colorado, water would boil closer to 105 degrees Celsius? This says 105. Who says closer to 95 degrees Celsius? Okay, so I'm seeing some votes on each one. I got a Paul Hewitt for you guys. Let's do a Paul Hewitt here.
Use a pressure cooker to prevent the boiling. That will prevent the cooling, and that will allow you to get more heat, more internal energy in your water and cook your food faster. That's what it's all about. Because more pressure, let's look at that. It's regular boiling. Let's not look at the pressure cooker yet. I won't put the lid on, okay? This is just regular boiling. Let's use, what's the temperature at which water boils, gang? Is it 100 degrees Celsius? Is that right? Let's suppose we get to 98 degrees Celsius. Now the water molecules, they're going a lot faster than they were at 78 or like that. Isn't that true? Okay, now they're 98. Now those water molecules are all banging around there. A little group of them says, hey gang, let's cut out. Let's form a little bubble. Let's be buoyed to the top and let's cut out. Let's steam it out right now. And so what they do is they form a little bubble here. And you know what happens when they form that little bubble? 30 kilometers of air, honey. 30 kilometers of air are squashing down. Squash right down and smash that bubble right back down to smithereens. The air pressure outside is simply too intense. to allow that bubble to form. Those molecules are going to have to go faster than that to exert enough pressure to overcome the pressure mainly of the atmosphere, let alone this height right here. So that's what happens. So the water then, since it's not cooling, the water goes up to 99. And the water molecules say, hey, let's try it again, gang. They cut out like this. And what happens? Whole atmosphere up above says, no, you don't. Smash. Smash them right back down. What happens? No cooling. The water heats up more. Now the molecules are more energetic, right? Will exert more pressure when they form a bubble, yeah? Now they form a bubble. Atmospheric pressure up above says, oh, no, you don't. Smash. Whole bubble says, oh, yes, we do. Squash. Because now the bubbles are pushing out with enough pressure to overcome the atmospheric pressure plus the pressure of the water. And that's the temperature at which boiling takes place at sea level. Now you go up in the mountains where you're closer to the top of the air. Does the atmospheric pressure push as hard? No. So boiling should take place at a higher temperature or a lower temperature. Does it make sense, a lower temperature? Isn't it neat how physics makes sense like this? See? And if you keep taking the pressure away, pressure away, you get boiling at room temperature and below.
Right. Okay, are you guys good with that? Right now, the rest of this he explains something, but I got a video for it, so it's better to see. Right, he's going to talk about where'd my video go? About reduced pressure boiling. Right. So, how much? What does it? What does it take to boil water? And it's not just the temperature. See, you don't actually have to put water on the stove to make it boil. Guys, watch this. You see some water being poured into that beaker right there, right? And they're doing here is they're vacuuming out all the air. It's like a vacuum chamber. You see that? You see that water boiling? See that water boiling? Right. Hey guys, question for you guys. If you touch that boiling water, what temperature would it feel like?
Room temperature.
Room temperature. It sure would. It wouldn't be hot at all. It wouldn't hurt you. What it's called you. It's just room temperature, right? But if you think back to what he was saying, because remember, here, show you guys this visual too. Look at this diagram. The whole time that the water is boiling, which is this flat part right here, isn't the temperature stuck? Right? But wait a minute, we got a stove flame underneath it, for regular boiling back in your kitchen, right? Hold on, we're putting energy into it, but the temperature is stuck. I think that boiling is allowing an equilibrium to be reached. Isn't sort of Paul Hewitt refers to boiling as a quote unquote cooling process because it like undoes what the flame underneath the pot of water would do, right? Right. Okay, and if that's true, going back to this reduced pressure boiling, right? Do you think that this boiling right here is taking energy out of that water? So it started off as room temperature, but guess what's happening to the temperature while it's boiling? Are you sure about that? Yeah, guys, it's taking energy out. What does that do to the temperature? Decrease? Lowers the temperature. In fact, if it keeps lowering, it's still boiling. If it keeps lowering, what eventually happens to the water if it gets too cold?
It
Freezes. Is that ice? What is that? Get that out of there. Is that ice? Oh, it is. It boiled until it froze. From reduced pressure. At no point was that ever hot. It started off as room temperature and it just got cooler until it froze over. All right, you guys see that? So that's pretty cool. All right, so let's look at a full map because everything on this page is at 1 atmosphere of pressure. Yeah.
Does that mean when they say like if you go into space your blood will boil, you won't get hot, it'll just
Yeah. You guys ever heard that? Right. Yeah. If you walk into a vacuum chamber with vacuum of space, you would boil away. Like the saliva on your tongue would boil, and all your blood would boil away. Right? Not because you were hot necessarily, but because of lack of pressure. Yeah, absolutely. That would be. Okay? There's a story you guys might be able to find on the internet. There was a guy decades ago. I think it was NASA chamber. They were testing an astronaut suit and had a tear in it. And he went to a vacuum chamber. They pulled out the air. Right. And that happened too. Is the saliva in his tongue started to boil. Now he passed out. He ended up being okay, like very luckily. I think he had like an earache or something for a day or something. He's super lucky that he wasn't more hurt than that.
the fluid in his ear must have started boiling too.
Probably so. Yeah. Right. Yeah. All right. So here's a fuller picture. Here's pressure and temperature. Right. Now you guys see temperature scaled linearly. Okay, so that's right. But I do want you guys to make note of the pressure scale. Do you guys see this? Guys, we're going from 1 pascal to 1,000 to 1,000,000 to 1,000,000,000 to 1,000,000,000,000. Guys, is that a linear scale?
No.
No, it's you call it a logarithmic scale. And this whole graph might be called semilog. Semilog because one axis is scaled exponentially and the other is linear. Is it? Right. So let's make our way around this. I got some red bars here. Now this horizontal red bar is 1 atmosphere. Is that what you guys are sitting in right now? 1 atmosphere pressure? Right. And these two verticals are at 0 degrees Celsius, 100 degrees Celsius. Right. Something like that. So right now in this room, guys, could you guys point where you are in this room on this diagram? Right. We're between, or you're, okay, so you know you're sitting at 1 atmosphere, so somewhere on this line, right?
Yeah.
Right. How many degrees Celsius approximately in here? Is it in the 20s maybe? The low 20s? I think it's in the low 20s, right? Which is what, about a fifth of the way between 0 and 100? So probably right where my pin is. You guys see that right there? So water in this room would naturally be what state? Liquid, right? And there's two ways to boil the water. Guys, what's one way to boil the water? You could increase the temperature. That's going which way on this diagram? To the right until, there it is, 100 degrees Celsius. Now it boils. It turns to gas. Okay. What's the other way again to also boil water? You just saw the video?
Lower the atmosphere.
Lower the pressure. Yeah, that's going straight down. There it is. It crossed right over here. You can boil that way. Okay. And then if you want to see the full map of where is it ice or liquid water or steam, there it is. Right. Hey, what is this point right here? Okay. Guys, can water exist as a solid, liquid, and gas at the same time? You guys want to see some boiling snow? Oh, triple point. Let's check out some boiling snow here. Here we go. Truth be told, the video you guys are about to see is not actually water. I forget what it is. It's some other chemical, but it's the triple point, so it's the same concept, right? So it's really hard to hit the triple point, kind of like trying to balance a pencil on its tip, right? Always wants. Right? It's hard to get it exactly, but okay. There's a liquid to solid transition. You guys saw, right? They're hitting all right around this triple point. You guys ready to watch that ice boil? There you go. Hey, look at that. See, they're hitting right all around that triple point. Yeah, look at that. Got some boiling snow going on. Ooh, it's pretty cool, right? Boiling snow. All right, you guys ready for Kahoot? I'm gonna pause this video, give you guys a minute to hop on Kahoot. All right, we're back recording. Yeah, thank you for hopping in pretty fast, and here we go. All right, heat. What have I been telling you guys is heat. Yeah. Start small font. Oh, hey, I can make that bigger. All right. Good to know. Oh man, all these years I've been teaching. Just realized I can make this bigger. All right. Okay, yeah, so yes, heat is the transfer of thermal energy. Yeah, due to a temperature difference. You guys remember if you put a hot block next to a cold block, the hot block's going to transfer some thermal energy to the cold block, right? And that transfer of thermal energy is called heat. There you go. That little technical definition there. There you go. All right. All right, getting points on the board. Yeah, there's all these are different ways to quantify it. Let's go through what these are. Now, you guys know what a joule is. You guys know 1 joule is 1 Newton times 1 meter. I think it's what? Kilogram meter squared per second squared. Okay. You guys remember conservation of energy from last semester, right? But how some of these other ones? Guys, does anybody know what lower case c calorie is? Do you guys know what that is? Guys, what is one lowercase c calorie?
Energy. Potential energy stored in
Like what? Like one. The definition of 1 calorie. Like who? Why they calorie? Oh. Right. Okay, so guys, 1 calorie is the amount of energy that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, Now, because what if you're looking at a nutrition label? You go to the grocery store, you look on a box, and it says how many calories is the food, right? Technically, those are kilocalories, or capital C calories. If you see capital C calorie, that's really actually thousands of calories because 1 calorie is such a small number, right? So, like, if you're going to eat 2,000 food calories, that's actually 2,000 kilocalories. Okay. And one more detail here is so if these are all forms of energy, you should be able to convert. So 1 kilocalorie, like 1 food calorie, is equal to 4,184 joules. Hey, and that number should look familiar too from that change of phase diagram you guys saw. Right. Or I guess 1 regular calorie could be 4.184 joules. All right. So next one. All right. Specific heat capacity. Ooh, remember that calculation we did at the end of yesterday and beginning of today? What is we were using the lowercase c for specific heat capacity. What is that? Yeah, the internal energy needed to change the temperature of 1 gram of substance by say 1 degree Celsius. We'd say or 1 Kelvin, same thing. Right. So you see right here the C. So for liquid water, it's 4,184 joules per kilogram Kelvin. Right. And yeah, throughout these, anytime you're within a single phase, right? Like that's for ice, it's a different value. Here it is for liquid water. There it is. There's that number showing up. Okay. Right. So how much energy does it take that's going to around this graph to change by 1 degree? That's like going up on the graph, right? So you think like the reciprocal of that slope right there. It's related to how steep is the slope.
Mr. Griffin,
Oh,
I'm
yeah.
gonna post this Kahoot online.
Yeah, I'll post this for you guys. Okay. All right, we got Spencer, Kyan, Gian, Talia, Spacer. The reason an ocean's temperature does not vary much from season to season. Ooh. Let's figure this out. Uh, okay, yeah, it has to do. Oh, hey, pretty good. Yeah, some of you guys have this. Has to do with the high specific heat capacity of water. Okay. Now, this links to something I was telling you guys about earlier today. Okay. Remember, I asked you guys if you have a pot of water, what heats up faster on the stove, the metal of the pot or the water itself? And you say, oh, well, obviously the metal of the pot heats up faster. Okay. Okay. And numerically, it shows up as the specific heat capacity. Okay. Okay. So if you throw hydrogen out, I'll throw hydrogen out. Guys, what's the largest number on this table? Yeah, the liquid water number right here, right? Which means that it's most difficult to change the temperature of water. So water has a really stable temperature, right? And then solids will typically not. Right? They're easier to fluctuate. Okay? So, how about this? Guys, where do temperatures fluctuate more? Like out in the Midwest of the states or out on the coasts? Where do temperatures fluctuate more?
Middle.
Yeah, definitely Midwest, right? Has anybody ever lived out in the Midwest? Midwest, yeah, right. You get these crazy hot summers and these crazy cold winters, but here in Florida, it's like fairly temperate all the way around, right? It hardly ever hits 100 degrees Fahrenheit, and then our winters are typically pretty mild too. Yeah. So yeah, if you live surrounded by water, the temperature tends to be pretty stable, and vice versa. Right. I think it's a question coming up anyway. So here. All right, got Gian, Talia, Kyan, Spencer, Spacer. The largest extremes in temperature. Ooh. Like the largest swings, differences. Yeah, middle of the continent, like out in the Midwest, you guys just said. Did you? Right? Because you're just land surrounded by land. Do you guys notice that all these other options are surrounded by water? Ocean, coast, island, surrounded by water. Is that? Okay? If you're surrounded by large bodies of water, it's really hard to change the temperature of water. Right? Um, how about guys? Let's do some biology here. Biology.
do you have a stable temperature?
Yes.
Yeah, it's like yeah, 98, 99 degrees Fahrenheit, somewhere there. Okay, something like that. Yeah. Now, yeah, if it fluctuates too much, then you'll get sick and die, right? If you're like 105 fever or go at 90 degree, right? So, yeah, what guys, what are you mostly made out of? You're made out of about 2/3 what?
Water.
Water, 2/3 water. Hey, do you think that's good fat goes hand in hand? Right, you're made out of mostly water and your temperature has to be stable. Ooh. Mm. All right, got Kyan, and Johnny Sins, Spencer, Spacer. During very cold winter, water pipes sometimes burst. Why? Yeah, water expands when freezing. Okay. So go back a week or two ago in this class. You guys remember ice floats? Right, you guys remember ice floats because it's less dense? Ah, so it takes up more volume for the same mass. Oh, yeah, sure would, wouldn't it? Yeah. Um, I know my brother lives up north, and anytime they're gonna have a winter storm, they always have to like drain their pipes to be careful so that the water doesn't freeze and bust the pipes. Right. Reason you can hold your fingers beside a candle flame without getting burnt. Yeah, all those facts go hand in hand. Right, so convection currents could want to travel straight up because if you heat up the air, what do you guys know about the volume of air if you heat it up? It wants to do what? Expand, right? Expand. You guys remember ideal gas law, right? And if the air expands for some given mass, larger volume, what is its density? More or less than before? The density would be less than before, right? Because it's now it's expanded, right? Which makes it want to float up to the top, doesn't it? Float up. So actually, it wants to go straight up. Um, Here's a poor conductor. Like if you hold your hand to the side of the flame, right? That convects the heat well, right? Because what if you do this? What if you have a candle flame and you put your hand above the flame? Could that burn you? Much worse? Yeah, because now that heat's going straight towards your hand. But beside, it's not as bad. All right. Maybe you feel some like thermal radiation. Heat travels from the sun to man. How does heat get from the sun to Earth? Oh. Yeah, radiation. Okay. So you guys remember like electromagnetic radiation through the vacuum of space? Okay. So conduction is direct contact. Right? So if you like, touch metal directly, right? Convection has to do with bulk movement of fluids. Right? So if you have water in a pot and it's hot in the bottom and cold in the top, it's going to start circulating. Right? Yeah, radiation through space, electromagnetic radiation. That's how all energy gets from the sun to Earth, pretty much. All right. Reason light color clothes help keep you cool in warm weather is that the clothes of light color. Yeah, reflect a lot of energy. There you go. Okay, so the white, yeah, like white, right? Doesn't white reflect all the colors? Yeah. Okay, so yeah, if it's a hot summer day and you're walking around in the sun, guys, what's it better? Is it better to wear a black shirt or a white shirt if it's way too hot outside? Yeah, I would wear a white shirt because that reflects the thermal energy away. Right? The black absorbs it all. The white reflects it. Oh, which cools at a faster rate? Ooh, it's a little tricky. Pot of boiling water, or lukewarm water. Faster rate. Oh, yeah, look at you guys go. All right, wasn't sure how you guys are gonna handle that one.
The podium, please.
Podium.
Yeah.
All right, here you go. Podium. Okay. So
Yeah.
here, that's this one right here. Okay, so maybe I got some hot water. I got a thermometer here, and if I leave this alone for enough time, it eventually approaches room temperature. That's the environmental temperature right here, right? It's not going, right? But the question that you guys were just asked has to do with not a
specific temperature, but the rate change, like a rate change. Okay, guys, if I hold my ruler flush this curve, it's really steep at the beginning. That's like changing very quickly, right? And then here it's changing not as much, right? And then after a few hours, maybe it's changing hardly at all. Yeah. So if you look at the rate change, that's like holding your ruler flush. It's called a tangent curve. Yeah, or tangent line. Oh, here we go. Newton's law of cooling. It says that the rate of cooling depends on, there's the equation you guys just saw. The rate of cooling. Yeah, nice. Right. So there are a few factors, but only one was the correct answer there. So let's look at right. So here's the rate of cooling. Maybe this could be in watts right here, right? Joules per second, right? So transfer of thermal energy per unit time, right? Right. So here's the temperature difference. That definitely matters, right? This temperature difference matters. Right? What do you guys think A refers to? Take a guess. I bet you guys get this too. Here, help you guys out. So you guys see this pan of water right here? What if I have a pan of water?
Oh, area.
Yeah, surface area. There is surface area versus a cup of water. And what if it was the same amount of water in both of these? Guys, which one of these do you think would cool down faster? How about the pan? Because look at all the surface area. Versus a little cup of water is hardly any surface area at all. Yeah, you guys see that? You guys see that? Okay. So more surface area, the faster. Okay. And then this H is like a material property. Like if you had a pan of olive oil next to a pan of water, those would act differently. All right, all right. A cup of hot coffee will cool faster if yeah, we hadn't talked about this. Some kind of black body radiation, like if you have yeah, in this case black coffee, it could both absorb and also release energy faster. Other than there. Made the cut for Kahoot. Yeah.
Yes.
Planet Earth loses heat primarily. Ooh, we know how it gets most of its heat energy. How does it lose the heat energy? Yeah. So we import energy by radiation from the sun, right? Okay. But then, here, guys, if the Earth, what is the Earth surrounded by? The vacuum of space? Yeah, nothing. Vacuum of space. So how's the energy get out? Because if all we did was just import energy from the sun, wouldn't the Earth just necessarily get hotter, hotter, hotter? Right? But there has to be some kind of equilibrium, right? So where's the energy go? Right? It also radiates away into space, right? There's no okay. These other ones require material properties. Are you guys okay with it has to radiate away? Right? Because we're surrounded by the vacuum of space. All right. All right. Condensation occurs when a matter changes from condensation. Yeah, gas to a liquid, which if you're paying real close attention, did show up on this one right here. Guys, it's right here. Right. So you're going from a gas to a liquid. Okay. You guys ever notice that, say, like in the morning, maybe it's been really humid because we live in Florida, and then maybe it's been kind of a cool night, and then in the morning there's dew all over the grass. Right, that's an example of this, going from, say, water vapor to liquid, right, like that. All right. Boom. Clouds form when warm air. Yeah, it's a three-part process. Right, so water warms up, becomes water vapor. It's got to rise, expand, then chill. Now you got a cloud with lots of little water droplets. Holy above. Oh yeah, holy above. When water freezes, ooh, making it colder, colder, colder. What's happening to the energy? It's getting colder.
Yeah. There you guys go. Right. It has to give away energy to its surroundings, or you can say its surroundings are taking the energy out of it. Right. Okay. Yeah, it's losing thermal energy. Okay. So here, got a visual. Right. So on this graph, we're going from say like this point here to this point here, right? It's losing internal energy, so it has to give that energy away from the first law of thermo. All right.
Like you read it?
I got Kyan, Johnny Sins, Benny Yen, Spacer, and Odera. Atmospheric pressure increases the boiling temperature of a liquid. Ooh. You go from Denver, Colorado, down to sea level. Right. So it'd be the other way around, right? Right. So the story we did with Paul Hewitt is if you start at sea level and go up into the mountains, you need less temperature to boil. Well, if you start in the mountains, maybe it boils at 95 degrees Celsius. So you come down to sea level. Now the necessary boiling temperature would increase, right, from 95 to 100 degrees Celsius. Right? Like up in Denver, Colorado, water boils at 95 degrees Celsius. Down here at sea level, it could be 100 degrees Celsius, right?
Yes.
So more pressure. All right. Kyan, Yahoo, Johnson, Spacer, Nadera. When snow forms, air becomes warmer because yeah, changing from vapor to solid gives away energy that's going from somewhere on the right of this curve to somewhere on the left of this curve. Think of it that way. All right. All right. I think I gotta step this up a little faster. We got what, about 8 questions left? You want to cook boiled eggs in the mountains. Ooh. Boiled eggs in the mountains. Yeah, okay, so the best answer is for a longer time. Right. So nobody picked a hotter flame, and the reason that's not the best answer is because yeah, you could turn the flame up, but the water temperature is like stuck at 95 degrees Celsius regardless. Right. You know, 'cause yeah, you just need to boil for a longer time. Yeah, up in the mountains, right, where you can't get the water as hot. Can't get the water as hot in the mountains. Right. You guys get that longer time? All right. Lowest possible temperature in nature. Lowest possible temperature in nature. Yeah, basically 2 correct answers. Right, so 0 Kelvin, right, but also negative 273 degrees Celsius. It's like negative 273.15 something, but it's around that. Yeah, so both of those would be good answers, right? These other ones, the Celsius and Fahrenheit, are just kind of arbitrary values. Right. Celsius and Fahrenheit can both go negative. So. Right, volume of air has temperature 0 degrees Celsius. An equal volume of air that's twice as hot. Twice as hot. It's not twice as hot. Okay, 50-50 split there. Here, give you guys a visual here. Guys, if you're sitting at 0 degrees Celsius and you double that, well, careful, you can't just double 0. First, you have to convert to what? Kelvin. And 0 degrees Celsius is how many Kelvin? 273. Because it's a straight conversion. All you need to do, Celsius to Kelvin, is simply add 273. Right? Don't worry about the 0.15 in this class. Okay? Right. Then, if you double that, guys, 273 times 2, is that 540 something? 540 something? Right? So now we're up at 540 something Kelvin. Then if you want to convert back to Celsius, you subtract 273, and that gives you 273 degrees Celsius. Okay? Right, little few part process there. Right? No, because when you get those puzzles on Thursday and there's a sub, and it says something about the temperature increases by some factor, you have to use Kelvin, right? Can you guys convert to Kelvin first before you push temperature through some multiplier? Right? Convert to Kelvin. The first law of thermo is a restatement of the Conservation of energy. Yeah, energy is conserved. You cannot create or destroy energy, but you can use it for accounting. Right? Now we just have thermal energy. That's the only addition now from last semester. We got thermal energy. Adiabatic processes, which involves no mass or heat exchange with surroundings. What do you guys think they're looking for? Yeah. All the above. All the above. Oh, yeah. Sorry, but it's not going through. Got Johnson's, Cayenne, Midnight Yahoo, Spacer, and Dara. Greater difference in temperature between input and output reservoir of a heat engine. Ooh, greater the difference in temperature. What do you guys think? Right. Yeah, the greater the efficiency. You guys remember I had that Stirling engine? Oh, I get my Stirling engine model up here. Yeah, Stirling engine. Or okay. You guys remember the other day I ran the Stirling engine by putting a cup of hot water underneath it? You guys remember that? Cup of hot water? Right, and it started to rotate. So it started spinning. It's fun for a long time. I think all the way to the end of class, right? Oh, right now there is zero temperature differential, so it's not even spinning at all, right? But I think the greater the difference in temperature. And here's an equation to back this up. Now this is Carnot like ideal efficiency. Right. I may have put this question on your puzzle packet. Okay, so if I say what's the efficiency of an engine between say like 10 degrees Celsius and 1,000 degrees Celsius? Okay. Can you guys first convert to Kelvin? Can you guys do that? Guys, do you want to put Celsius in here or Kelvin?
Kelvin.
Kelvin. It has to be Kelvin. Has to be Kelvin. We're taking a ratio, right? And then do 1 minus. Okay. I think that question might become a. Can you guys jot that down on paper? I think that's one of the questions about to pop up on Kahoot. So the efficiency, that's what eta is right here. Eta is 1 minus the ratio of the temperatures, but the temperatures have to be in Kelvin. Okay? Right. Can you guys do that? We're going to find out pretty soon here. Find out pretty soon. We got 3 questions left. 2 identical blocks of iron, one at 10 degrees Celsius, one at 20 degrees Celsius, put in contact. Suppose the cooler one cools down even more, and the one warms up even more. They changed by 5 degrees. Okay. Now, realistically, that would never happen because that would be a violation of what? Hmm. Yeah, only the second law. Okay. The first law is actually safe because if one drops by 5 degrees, the other picks up by 5 degrees, same material, same mass, yada yada. Right. The first law is actually safe in terms of quantity of energy. But the second law has to do with, you guys remember like time order processes or something about increasing entropy as time moves forward? If you did an entropy calculation, that would totally mess up with that. Okay. Yeah. Because the second law has to do with time order of spontaneous processes. Running a refrigerator with the door open in a hot room. Ooh, I might have to round back to this one tomorrow. Take a guess. What do you think? This is probably going to be a final exam question. Yeah, okay, so guys, more on this tomorrow. But one more question. Here we go. For the win. Who will win? Yep, exactly what I promised you guys. Ideal efficiency for an engine between. Oh, and I gave it to you in Kelvin. All right, how nice of me. Can you guys do 1 minus? You guys got a calculator? Do 1 minus 310 over 2050. Okay? You do 1 minus 310 over 2050, and it should give you one of these answers. Who gonna win the Kahoot? Did you guys get it approximately 0.85? Somewhere there? Yeah. All right, let's find out. With the bronze, Benjamin Netanyahu. With the silver, Spacer. And the gold, Anna and Jara.